Okay, so far in chapter 4, we have been discussing the secrets of solving second order linear differential equations, right? So there are several types of equations now. First of all, what we learned is we learned how to solve homogeneous differential equation. The solution is called complementary function. Yes. And then we found this complementary function by using auxiliary equation method, right? Try to take the quadratic function or the polynomial that gets you factorize, or you use the quadratic formula and you find roots and you find this fundamental set of solutions. Good. But then you have one restriction. Your differential equation should have constant coefficients. Okay. Then we learn another method where we can solve non-homogeneous differential equations. But to do that, first you have to solve the homogeneous form. You use the auxiliary equation, you get the fundamental set of solution, and then remember, you make a guess, then you solve the full problem, right? You find this particular solution. But again, it's necessary that in your differential equation, you should have constant coefficients. How about if you have non-constant coefficients in your differential equation? That means you have functions of independent variable as coefficients in your linear differential equation. How can we solve them? Well, we are going to learn one powerful method called variation of parameters to do that. Okay? All right. So in the variation of parameters method also, you have to first solve the homogeneous version of the same differential equation. Okay, so you need to figure out the fundamental set of solutions for this differential equation. Okay, all right, so you need to know, for a second order differential equation, you need to know y1 and y2. Okay, so let's say that you know this y1 and y2. Okay, that is our assumption. It should be given to you. If you know y1 and y2, then we can write the complementary function c1y1 plus c2y2, right? Okay, so all what we need to know now is how to find yp, particular solution. Here in the variation of parameters, the biggest assumption is you assume your particular solution is like an unknown function u1 times y1, the first solution of the fundamental set of solutions, plus u2 unknown function times y2, the second solution of the fundamental set of solution. So this is the big assumption that we make in our variation of parameters method. Okay, so now you will be able to learn the full method in the next couple of videos, but that is the big assumption. Okay, so few key things before we move on. You have to have your differential equation in standard form. So that means you take your differential equation and you make sure the coefficient of the y double prime term is 1. So if you have a non-1 coefficient, you divide by that coefficient and you get this standard form of the differential equation. Okay, so variation of parameters method, the biggest assumption is assuming you know y1 and y2. Sometimes you might have to find this y1 and y2 depending on the question. We will see questions. So you use your y1 and y2, the fundamental set of solutions for the homogeneous differential equation. We use them to find the particular solution. So really we assume our particular solution is in this form and we are shooting for u1 and u2. If we can find u1 and u2, then we can find the particular solution by multiplying like this. Okay, so that's a big idea, little bit similar to the reduction of order method. Okay, all right, so let's learn the methodology in the next video. Thanks.